Hello and welcome. Today we're going to pull back the curtain on the secret life of waves. You know, they're everywhere, carrying sound, light, all kinds of information. But they have these really cool behaviors that honestly explain so much about the world around us. Okay, let's jump right in.
So we're going to start with a puzzle, one that you've probably experienced 1,000 times without even thinking about it. How is it that you can hear someone chatting just around a corner, but you can't see them until they step out? It's a great question, right? And stick with me, because by the end of this, you're going to know exactly why that happens.
All right, so to solve this little mystery, we first need to understand our main suspect, the wave itself. We've got to know what it is and how it works before we can figure out its secret moves.
So what even is a wave? Well, at its heart, it's just a disturbance, a vibration. But its main job, its entire purpose in life, is to move energy from one spot to another. And the cool part is, it does this without actually moving the stuff it's traveling through. You know, think about ripples in a pond. The water itself just kind of bobs up and down, but the energy from that splash, that travels all the way across.
Now here's the thing. Not all waves are built the same. They have these unique characteristics, almost like vital stats, that completely control how they behave out in the world. And if we're going to crack our case, we need to know what those stats are.
Okay, so let's start with the two main types. Over on the left, you've got transverse waves. This is where the vibrations go up and down, at a right angle to the direction the wave is actually moving. Shaking a spring up and down is the perfect picture of this. Then on the right, you have longitudinal waves. Here, the vibrations push and pull in the same direction as the waves travel. Think of squishing a slinky in and out. And guess what? Sound is a classic longitudinal wave.
Okay, so let's break down those vital stats. First up, wavelength. Super simple. It's just the distance from the top of one wave to the top of the very next one. Then you have amplitude. That's the wave's height, or its power. When we're talking about sound, amplitude is just loudness. And finally, there's frequency. That's how many waves zip past a certain point every second. For sound, a higher frequency means a higher pitch. So these three, wavelength, amplitude, and frequency, they're basically the wave's DNA. They define everything about it.
All right, it's time for our first big clue. One of the most basic things that waves do is bounce off stuff. And this behavior has a really simple name, reflection.
And this bouncing, it's not random at all. It follows a super strict rule called the law of reflection. All it says is that the angle a wave hits a surface is the exact same angle it bounces off at. It's precisely why you can see your reflection in a mirror. Light waves are just bouncing off that surface and coming straight back to your eyes.
So what's a perfect, everyday example of sound reflection? An echo, of course. An echo is literally nothing more than sound waves from your voice traveling out, hitting something big like a cliff or a wall, and bouncing right back to your ears.
But, you know, you don't always hear a distinct echo, right? Well, for our brains to actually process that reflection as a totally separate sound, a few things have to be just right. First, there needs to be a time delay of at least 1/10 of a second. Second, the surface it's bouncing off of needs to be pretty big and hard. And of course, the original sound has to be loud enough to actually make the round trip.
So how far away does that surface have to be? Well, if you do the math, knowing the speed of sound is about 340 meters per second, for a sound to go out, hit something, and come back in that minimum 0.1 seconds, that surface has to be about 17 meters away. If it's any closer, our brains just kind of smush the reflection and the original sound together. Okay, let's move on to our second clue, and honestly, this one is the key to solving the whole puzzle. It's called diffraction, and it's the incredible ability of waves to bend or spread out.
Diffraction is what lets waves do that sneaking thing, getting around corners or fanning out after they go through a small opening. It's a totally natural thing for any wave to do, but how much it bends is not random at all. There's a very specific rule at play.
And here it is, the golden rule of diffraction. The amount a wave spreads out comes down to one simple thing: the relationship between its wavelength and the size of the opening it's trying to squeeze through. You get the most dramatic bending, the most spreading, when the wavelength and the gap size are pretty similar. If the gap is way, way bigger than the wavelength, the wave just sails right on through without much change.
Okay, the moment of truth. We now have all the evidence. We know waves can bounce, and we know they can bend. So let's put it all together and finally solve that mystery of why you can hear but not see around a corner.
Just look at this side by side. On the left, we have sound waves. A typical sound wave you might hear has a wavelength of roughly a meter. Now look at the right, light waves. Their wavelength is microscopic, literally thousands of times smaller. Now picture a normal doorway in your house. And there you have it. The secret is the wavelength. A sound wave's meter-long wavelength is a fantastic match for the size of a doorway. That perfect match causes a ton of diffraction, letting the sound waves spread out and bend around the corner right to your ears. But for light's teeny tiny wavelength, that same doorway is like a massive wide-open gate, so it experiences almost zero diffraction and just travels in a perfectly straight line, right past you. Puzzle solved!
So, now that we get these principles, let's check out how both nature and technology have put them to absolutely incredible use, especially that idea of echoes.
And it turns out, nature is the absolute master of using echoes. Bats are a perfect example. They can navigate in total darkness using a system called echolocation. Just like this quote says, they send out these high-frequency chirps and then listen for the returning echoes to build this incredibly detailed mental map of everything around them. We're talking precise enough to catch a tiny mosquito in midair.
And what did we humans do? Well, we saw that and said, I want one of those. So we built a machine that does the exact same thing. It's called sonar, which stands for sound navigation and ranging. It's basically our own man-made echolocation, but built to see underwater.
And the process is so elegantly simple. First, a transmitter sends out a little pulse of sound, the classic ping. That sound wave travels through the water until, bam, it hits something and reflects. Then a detector picks up that returning echo, and a computer precisely measures how long that whole round trip took.
And get this, the math behind this amazing technology, it's the exact same simple formula we use to figure out that 17-meter distance for an echo. You just take the speed of sound in water, multiply it by how long the echo took to return, and then you divide by 2, because, the sound had to go there and back. That's it.
And with that one simple principle, we can do some incredible things. We use sonar to map the entire ocean floor, to find shipwrecks lost for centuries, to help fishermen find schools of fish, and even to track submarines. It is literally our set of eyes for the deep, dark ocean.
So, we've seen that understanding how waves bounce and bend isn't just about solving a fun physics puzzle. It lets us explore worlds we could never see otherwise, from hearing around a corner to charting the deepest parts of the sea. It really makes you wonder, doesn't it? What else is out there that we could see?